Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 3. In this lecture, we'll discuss sinusoidal functions. This topic is covered in Chapter 15 of our textbook by Surway and Jowett. Recall that we're interested in understanding the precise behavior of a simple mass spring system. What makes a mass spring system simple is the fact that the only force acting on the mass is the spring force. There's no friction, there's no drag, and there's no driving forces. We will turn to those other effects in future lectures, but for now we're interested in simple mass spring systems only. We decided that the behavior of such a system is described by this second-order differential equation, and last time we decided that the solution to this differential equation is this function here. So the position of the mass as a function of time is equal to a cosine omega t plus phi. Now notice that there are three important parameters in this function, a, omega, and phi. If you want to actually calculate the position of a mass as a function of time, you have to be able to calculate numerical values for a, omega, and phi. Last time we decided that calculating omega is relatively easy. Omega is simply equal to the square root of k over m, where k is the spring constant and m is the mass. To calculate a and phi, one needs to know what the initial conditions of the problem are. As you will see over the next few lectures, trigonometric functions like the cosine and the sine functions play an important role in describing oscillations and also waves. So it'll be very important for us to be comfortable, in fact fluent, with the use of trigonometric functions like the cosine and sine. So in today's lecture, our goal is to simply become very comfortable with cosines and sines and to better understand the physical meaning of these parameters a, omega, and phi. We have used the cosine function to describe the position of a mass spring system. The cosine function turns out to be very similar to the sine function, and these functions collectively are often referred to as sinusoidal functions. So any function that basically behaves like a sine function in an oscillatory or periodic manner is generally described as a sinusoidal function. Sinusoidal functions can be written in many different forms. These forms are equivalent to each other, and it's important for you to recognize these equivalent forms. For example, we will often describe the motion as a cosine omega t plus phi, but you need to recognize that the same function can also be written as a cosine omega t plus phi plus or minus 2n pi, where n is an integer. So what I'm saying is that you can add 2 pi or 4 pi or 6 pi or 8 pi or any even number of pi's to the argument of the cosine function without changing the function. And that's essentially a consequence of the fact that the cosine function is a periodic function. It repeats itself every 2 pi radians. So if you take a cosine function and shift it to the left or to the right by 2 pi radians or 4 pi radians, for example, then you'll essentially get exactly the same graph and therefore an equivalent function. You can also write the same function like so, by multiplying the argument, the thing inside parentheses, by a minus sign. So you can put a negative sign in front of the omega and the phi, and you will see that the graphs of all three of these functions look exactly the same. They are indistinguishable, so they all describe the same function. This second identity here is a consequence of the fact that cosine of, for example, minus 45 degrees is equal to cosine of 45 degrees. You can also do something else. You can also multiply the entire function by a negative sign, so put a minus sign in front, and then shift the argument by pi radians. This is a consequence of the fact that you can take a cosine function and flip it upside down. That's what the negative sign here does, and then shift it to the left or to the right by pi, and that again gives you the original function. You can also do a combination of the last two operations. You could put a minus sign in front, multiply the whole function by a negative sign, and then at the same time multiply the argument by a negative sign. So put a minus sign in front of the omega and the phi and the pi, and once again you get the same function. Of course, here I've been talking about the cosine function, and that's what we'll do for the most part by convention. We like to use the cosine function, but you can also use the sine function. The sine function really isn't that different from the cosine function. If you look at their graphs, you'll notice that a cosine function and a sine function look identical, except that they are shifted relative to one another. So it turns out if you shift the sine function by pi over 2 radians, you'll basically get the cosine function. So this form is also an equivalent function to this original function here. On an exam, if you wrote any one of these answers in response to a question, you would get full credit. However, we will adopt some conventions just so that we could all be on the same page. By convention, we'd like a to be a positive number, so we usually don't like negative numbers in front of the cosine function. By convention, we usually choose omega to be a positive number. It doesn't have to be positive, but it's nice to choose one of these forms where the number in front of time is a positive number and not a negative number. And again, by convention, we usually choose phi to be between minus pi radians and plus pi radians, so between minus 180 degrees and plus 180 degrees. You certainly don't have to use these conventions, but using these conventions will often help you better understand why, for example, I present the solution in a particular form and not in any of these other equivalent forms. Recall that the behavior of a simple mass spring system is described by a cosine function that involves three parameters, a, omega, and phi. Up until now, we've been talking about these three parameters just as mathematical constants, but we need to understand their physical meaning a little bit better. Parameter A is known as the amplitude of the oscillations. Given a graph of the oscillations, the amplitude is the maximum value of those oscillations. So if I gave you the function and asked you to draw the graph, you would know how high the graph needs to go. And if I gave you the graph and asked for the function, you could maybe read off the height of the graph, and then that would be the amplitude. Physically, the amplitude controls the maximum distance from equilibrium. So if I told you that the amplitude is, for example, 5 centimeters, then I'm basically telling you that the mass can go as far as 5 centimeters from its equilibrium position. The second parameter that's important to us is omega. Omega is known as the angular frequency of the oscillations. Omega controls the length of time between two peaks. So given a graph that describes the oscillations, position versus time, if you're interested in the length of time that passes between one peak and the next peak, you would need to know what omega is. A little more precisely, the time in seconds that elapses from one peak to the next is actually equal to 2 pi over omega. So if I told you an oscillation has a very high angular frequency, I'm basically telling you that omega is large, and therefore the period of time between this peak and this peak is very small. In other words, the oscillation repeats itself very often. Remember, when I speak about one peak and the next peak, what I'm really talking about is the mass being at maximum displacement at one instant in time and then reaching the same maximum displacement at a later moment in time. The period of time that elapses between those two positions is going to be inversely proportional to omega. Here I'm talking about the peak to peak interval, but of course you can also go from a valley to a valley. Those two numbers would be equivalent. The third important parameter in this context is phi. Phi is known as the phase constant. The phase constant controls the horizontal shift of the graph. In other words, the phase constant basically tells you the starting point of the graph. A cosine function ordinarily starts at its maximum value. Looking at this blue graph here, you can see that it starts at t equals 0 down here, which suggests that the standard cosine function must have been shifted. The whole graph in this case is shifted to the left by phi over omega. Here we have to be a little careful. When speaking about this function here, people often say that the cosine function has been shifted by phi radians. However, if you want to actually draw a graph, you're not interested in radians, you're interested in seconds. Notice that the horizontal axis is the time axis. So we're interested in something that has units of time, like seconds, not units of angle, like radians. So if you want to know how many seconds the graph is shifted to the left, you need to take phi and divide it by omega. So take the phase constant and divide it by the angular frequency, and that tells you how many seconds the graph has to be shifted. If the number is positive, then the shift is to the left. If the number is negative, then the shift is to the right. Here, I'm imagining that the coordinate axes are fixed and I'm shifting the graph to the left or to the right. Some people adopt the opposite convention. It helps to pay attention to the units in this context to avoid confusion. The units for phi are often radians. So when I put square brackets around the quantity, I'm talking about the units for that quantity. And in the SI system, the units for phi are radians. The units for omega, on the other hand, are radians per second. And the unit for phi over omega is going to be radians divided by radians per second, which gives us seconds. So if you want to know how many seconds the graph has to be shifted to the left or to the right, you can't just look at phi, you have to look at the ratio of phi and omega. The three parameters A, omega, and phi, amplitude, angular frequency, and phase constant, help us describe the oscillations of a simple mass spring system. We've already seen that omega can be expressed as the square root of k over m, where k is the spring constant and m is the mass of the object attached to the spring. The SI unit of angular frequency is radians per second. It turns out there are two other concepts that are related to angular frequency, and it's important for us to be familiar with them because people often use them to describe oscillations. The first one is the concept of period. The period of an oscillation is the amount of time required for one cycle. Here, by one cycle, I mean one repetition of the motion. So imagine observing a mass spring system as it oscillates back and forth. Imagine starting at any point along its motion and then wait until the mass returns to exactly that same point with the same velocity, and that's one cycle. If you happen to have a stopwatch in your hand and you're timing the amount of time required to complete one cycle, then you are measuring the period. The period is denoted using capital T. Note that lowercase t is used for time, uppercase T is used for period, and we can calculate the period using this formula. The period is 2 pi over the angular frequency. Recognizing that the angular frequency itself is square root of k over m, we can calculate the period by 2 pi times the square root of m over k. The period is the amount of time, so the SI unit of period is the second. The second important concept for us is frequency. The frequency of an oscillation is the number of cycles per unit of time. So imagine setting aside some unit of time, like 1 second or 1 minute or 1 hour. Then imagine counting the number of cycles that are completed in that period of time. The number of cycles is referred to as frequency. Frequency is denoted by lowercase f, and it can be calculated using this formula. Frequency is simply 1 over the period, and recognizing that the period is given by this formula, you can calculate the frequency as 1 over 2 pi times the square root of k over m. The SI unit of frequency is cycles per second, and we often refer to a cycle per second as 1 Hertz, named in honor of German physicist Heinrich Hertz. So when we say that the frequency of an oscillation is 10 Hertz, what we're saying is that that mass spring system can complete 10 cycles in 1 second. It's important for us to be able to describe oscillations both in terms of functions and also in terms of graphs. In fact, it's important for you to be able to draw the graph if I give you the function, and write down the function if I give you the graph. So let's do a practice problem that should help with that. Write the function x of t based on its graph shown here. So we have a graph here that is describing the oscillations of a simple mass spring system. On the horizontal axis we have time in seconds, and on the vertical axis we have position in meters. According to this graph, at t equals 0, the mass begins at x equals minus 0.7. When it is released, it begins to move in the positive x direction, and then it reaches its maximum displacement. At a time of 3 pi over 2 seconds, it reaches its maximum displacement, and then it turns around and moves in the negative x direction. And then presumably it repeats this motion over and over again. So based on this information, based on this graph, write down the function that describes these oscillations. Now we've already determined that the solution to the mass spring differential equation is this function here, so this function should always be your starting point for problems of this nature. Of course, notice that this function has 3 parameters, a, omega, and phi, and we need to calculate the numerical values for these 3 parameters based on the graph. Of the 3 parameters, a is usually the easiest one to figure out because normally you can read it off from the graph. For example, I can see that at a time of 3 pi over 2, the graph reaches its maximum value, and that maximum value is equal to 1. That fact tells me that the amplitude must be in fact equal to 1. You can also say that this distance here is simply equal to the amplitude, so the amplitude should be equal to 1. The next thing we want to calculate is omega. Now you can't really read omega directly from the graph. However, you can notice that this graph does repeat itself. For example, at a time of minus pi over 2 seconds, the mass is located here, and then if you wait a few seconds, it returns to that position. In fact, at a time of 7 pi over 2, it returns to that position. The amount of time that passes is known as period. Remember that the period of an oscillation is the period of time it requires to essentially complete one cycle or complete one repetition. So I can calculate the period directly from the graph. I notice that the period is going to be final time, which is 7 pi over 2, minus the initial time, which is minus pi over 2, and 7 pi over 2 minus a minus pi over 2 is equal to 8 pi over 2, which I can simplify to 4 pi. So that tells me that the period for this oscillation is 4 pi. Of course, I'm not really interested in the period, I'm interested in the angular frequency omega, but I know that those two things are related. What I know is that the frequency is 1 over t, so the frequency for this oscillation is going to be 1 over 4 pi. And I also know that angular frequency is 2 pi times the frequency. So I have 2 pi times 1 over 4 pi, which tells me that omega is 0.5 or 1/2 radians per second. Now that I have omega, I can turn to phi. Phi is usually the trickiest thing that you calculate. It should be the last thing that you calculate among these three parameters in this type of a problem. To calculate phi, it's helpful if you choose a peak. You can also pick a valley, you can also pick a zero. However, a peak usually stands out and it's a unique point in the cycle within one oscillation of the system. So it's helpful to choose a peak and notice that the x-coordinate at that peak is going to be equal to the amplitude, which is 1. So what I'm doing here is choosing a peak and noticing that the oscillations achieve that peak at a time of 3 pi over 2 and that the x-coordinate is 1. So I can express that fact by saying that x at this particular time, 3 pi over 2, is equal to 1. Now I also have this equation here, and I can see that based on the equation, x at a time of 3 pi over 2 is equal to the amplitude, which we've determined to be 1, times cosine of omega t. We already know omega is 1/2 and t is 3 pi over 2. So omega t gives me 3 pi over 4 plus phi, and I don't know what phi is. But I can now figure out phi. I have two expressions here, and I can set these two expressions equal to each other and solve for phi. So you set 1 equal to cosine of 3 pi over 4 plus phi. You will have to isolate the phi by taking the arc cosine or the inverse cosine of both sides of your equation. Hopefully you know where the arc cosine button is on your calculator. Or better yet, hopefully you know that the arc cosine of 1 is just 0. And if you know that, then you can solve for phi, and you can find out that phi in this case is going to be equal to minus 3 pi over 4. So now we have the function. We can say that x as a function of t is equal to the amplitude, which we've determined to be 1, times cosine of omega t, we've determined omega to be 1/2, plus phi, and we've determined phi to be minus 3 pi over 4. Now note that at the beginning of this lecture, I told you that these sinusoidal functions can be written in many different forms. So you could add 2 pi to the argument, for example, and you would get the same function. You could multiply the whole function by a negative one, so long as you add pi to the argument. Or you can even write a cosine function in terms of a sine function. Here I've written down only one of those alternative forms. It turns out this cosine function can also be written in terms of this sine function by shifting one by pi over 2 radians relative to the other one. On an exam, you could give me either one of these solutions and I would count it as correct. If you have a graphing calculator or you know how to use a spreadsheet, you can also go and graph both of these functions, and you can see that those two graphs will look identical. And that is the end of this lecture. Thank you for your attention.